Before I begin, I would like to acknowledge Brian Cheadle and Kit Coleman, who hired me back in 1984. Um, Kit sadly has passed away recently, but Brian is here. I don't know whether to thank him or not. Maybe it was a good decision, maybe not. Who knows? I'm going to talk to you today about my book entitled An Engineer's Guide to Nuclear Reactor Core Materials. There are 16 chapters and 640 pages. It's a textbook about the physics of materials in nuclear reactor cores, but don't worry, I'm not going to talk about everything in the book, and we'll keep it mostly non-technical. Start with the motivation. There's a time in one's life when there is a critical mass of knowledge and experience that allows one to better understand a subject and make connections that one thinks may not be obvious to others. The problem with this is that you may be deluding yourself, although you would like to share your experience with others. You maybe just be stating the obvious, like this guy here who has a blinding flash of the obvious in a meeting. The best we can do is soldier on and move the puck around a little bit sometimes. In writing this book, I wrestled with some difficult concepts and would often think back to my physics lectures at Bristol University and realize years later that, oh, that's what that was about. Why didn't they just say it? Maybe they did. Maybe they did explain it. And I was just too dumb and ignorant to understand. With that in mind, I've endeavored to present the subject of the physics of materials and nuclear reactors in such a way that a younger me would understand, as well as any other young engineer scientist of average intelligence who cared to read the book. They have to be willing to accept that they have something to learn. Which brings me to Dunning-Kruger, which I prefer to call the Machiavelli-Schopenhauer effect, because these guys, Machiavelli and Schopenhauer, talked about the same thing hundreds of years before Dunning and Kruger. It is a principle relating confidence and competence that can be summarized as the more you learn, the less you know. That is, the more you doubt yourself. I realized that quite strongly when I was completing my Viva Voce exam at the end of my PhD. Basically, a Viva Voce means living voice. You end up, you've written a thesis and you defend it in front of a panel of professors who in principle understand and know everything about the subject. And they question you. And when they question you, you realize how little you know. And it's very embarrassing. So I passed. I don't know why, but I think I was probably in the bottom 10% of all the students that my supervisor had. But at the end of the exam, I was in his office and he looked at me and he says, "What's wrong, Malcolm? Why do you look so glum?" And I said, "You see that door?" And he said, "Yeah." I said, "I feel I could walk under it. I feel so small. Either walk or slither under it." And he looked at me and he said, he didn't smile, but he said, "Good, because if we let you go out of here thinking that you knew something, we would have failed." I understood that. I spent 45 years in research, and in the last 15 years, I was an R&D manager. I came across two types of people. Those who were receptive, that are willing to talk and listen, and those were unreceptive, and I class those people as willfully ignorant. There have been times in the past when a material issue arose in the reactor, and I was shocked at the ignorance of some of my coworkers. In those cases, a little knowledge is a dangerous thing, meaning they believe they know everything they need to know. I once said to a fellow middle manager at Connectrix, you know, you can lead an engineer to order, but you just can't make them think. I was so mad with them. To illustrate, to give you some examples, once there was a commotion at Chalk River about 20 years ago. There were some concerns because there'd been some measurements done, some tests on pressure tubing, and there was an unexpected result. It was high value. I'm not going to talk about exactly what it was, but anyway, this was S99 reportable, meaning it had to get relayed to the CNSC. Now, when I saw what was happening in email space, I sent an email to the group and I said, oh, I think I know what's going on. You may think it's an unexpected result, but it could be very expected depending on where you took the sample. If it was at 1 meter or 2 meters from the inlet and it was at 12 o'clock, I would expect that to be a high value. I didn't hear anything. 2 years later, a manager in a meeting, or one of the managers of the team it was in a meeting, and he said, look what my guys have just discovered. They deserve a medal. I said, oh, and it was basically what they discovered was what I told them 2 years previously. And I said to him, I said, well, why give them a medal? They've just reinvented the wheel. I told them that 2 years ago. And I had the reason to tell them that because I had data which would indicate that. Anyway, he looked at me and he said, well, maybe you just didn't explain it well enough. And my thoughts at the time were, well, maybe they just weren't willing to listen, as you were not willing to listen. More recently, I had an experience with a PhD student at Queen's, it was about 5 years ago, maybe a bit less. And he was working on density functional theory. And this was basically a theoretical study on the stability of certain phases. And I was asked to review, actually I was asked to be a co-author on his paper. And I read it, I read the first draft, and I said, oh, there's a problem here. There are two very good pieces of work that you've omitted. You haven't talked about them. And he said he thought that they were irrelevant. My response was, well, they're not irrelevant because they actually contradict their experimental data and they contradict your theoretical assumptions. What I thought was that, well, maybe this guy needs to have a few courses in science ethics. Not that there are courses in science ethics. How most people get their ethics, it's either natural or it isn't. Sadly, Queen's doesn't have the training to promote good science ethics. I'd like to mention a couple of my positive experiences with receptive people. Um, about 20 years ago, I had a summer student come join the branch for a summer, and he came to my office to introduce himself, and we talked a little bit, and then I realized he could benefit perhaps from a little pep talk, and I took him aside, and we talked for about an hour, 2 hours on the subject he would be working on and why he was doing it. At the end of the 2 hours, he looked at me and he said, "Oh my God, I've just learned more in 2 hours than I had in a whole semester at the University of Toronto, engineering physics department." Similar, on the same vein, about 5 or 6 years ago, I was at Idaho National Lab at the behest of the Electric Power Research Institute. They wanted me to oversee some experimentation that was ongoing that they were paying for, but was being conducted by Idaho. So I came in, we spent a week. I basically advised, watched what they were doing, and they finished their work. I'm not sure what the results whether the results were appreciated or not, but we were done. And I was in there on the Friday morning and basically saying goodbye, and the senior contract officer on the project asked me a few questions. He wanted to know a little bit about electron diffraction and defect analysis. And we spent about 3 hours in his office talking about those things. At the end of it, he looked at me and he said, "I've just learned more in 3 hours than I have in 3 years at Idaho National Laboratory." Now, if I had $1 for every time somebody had said that to me, I'd have $3. The next slide describes what I'd actually told the summer student, or mostly describes what I told the summer student. I put it in the form of a video because it's the best way to...
For many common metals, the best way to understand the structure and properties of the metal itself is to think of the atoms as being hard spheres. Now, metal atoms bond together by donating their outer shell electrons or their valence electrons into a common pool, and this allows them to stick together. Now, once we have this bond system in place, then the next level of bonding has to do with minimizing the energy of the system. And that can be achieved by packing the atoms together with the shortest possible bond lengths. And in this case, it's a close packed structure. And this is an example of a single layer of a close packed structure, and it has this distinctive hexagonal shape. So I'm going to think about the three-dimensional structure. Let's put down a first layer. I'm only going to. It's easier for me to use 3 atoms in this case, so I'll just use 3, because then I'm going to sit the next layer on top, which is my close packed layer, and I'm going to sit it like. Now, if I want to build up a three-dimensional structure, I can do it in 2 possible ways. I can either put the next layer of atoms on here, like that. And you'll notice this atom here is directly above this atom here. So if we call this atom, this layer, an A layer, and we call this layer a B layer, this atom, which has the same position looking down on the plane as this atom, we would also call that an A layer, because the layer designation letter defines where the position of the atoms relative to the whole lattice. So we have this ABA, what's called ABA stacking. And that's common, or that defines what is a hexagonal close-packed metal, this ABA structure. Now, the atoms don't have to, the third layer of atoms doesn't have to sit like that. It can go like that, or sit in this position, which is just as stable. In that case, we have A, B, C stacking. So there are three different positions for the different layers. So what defines what now is a face-centered cubic crystal structure, what distinguishes this from a hexagonal close-packed structure is simply the position of that third layer. So this is hexagonal close-packed, and this is face-centered cubic.
The slide summarizes what I've just presented there in the video. The thing to pay attention to is the fact that there are essentially two structures that one can obtain through close packing, which is the face-centered cubic or the hexagonal close pack structure. Now, these crystal structures account for most of the materials used in reactor cores, but they're unique because they're produced from the close packing of spheres. But not all metals are FCC and HCP. They represent 2 of 14 different possible atomic arrangements that define the crystal. 7 different crystal classes and 14 unique arrangements that have different centerings. It may seem boring to know this, or it may seem boring to study, but a little knowledge of crystallography can be a source of fun. I'll illustrate this here. When I was a student studying metal physics at Bristol University, one day I was walking with a small group of fellow students for lunch at the Students' Union. We just had some lectures on crystallography. One student at the group had studied at the University of Bath and hated Bristol. He said, "I hate Bristol. Look at all these buildings. They are so monolithic." I thought, hello. There's an opportunity for a joke here, because monolithic sounds a lot like monoclinic, and a monoclinic crystal is nothing like the slab-like shape that one would expect for a high-rise building, for instance. So I said, "Oh, I don't know. They look more orthorhombic to me." He then had 2 things to hate about Bristol: the town and me. It is important to know some crystallography if you want to understand all aspects of metal physics, including deformation. So I'm going to give you a very brief introduction to deformation as relates to metal crystals. Oh shit. Right now I would be demonstrating the shear from slip and from twinning and from magnetic transformation. That would take about 2 minutes, 3 minutes, and unfortunately I can't return. I don't think so. I don't think I can go back right now because this is recording. So I assume I've just told the audience that everything they need to know about how a dislocation slip. We're using a ball model in a displayed at the front of the lecture hall. So in this ball model, I refer to slip, twinning, and martensite, which are the 3 main processes one can apply to cause deformation of metal crystals. So I've been describing the deformation of single crystals, but engineering alloys are made from an agglomeration of crystals that we call grains. and they are bound together by metallic bonding at the grain boundaries. The boundaries are much stronger than the grains because the regularity of the atomic arrangement actually makes it easier to cause deformation. The underlying deformation mechanism within the grains involves dislocations. So what is a dislocation as far as metals are concerned? Just like someone may dislocate an elbow involving displacement of a bone from where it should normally be, dislocations in metals involves the displacement of some atoms from their normal positions. The dislocation is the line along which all the bonds have been broken. This is known as a line defect. Now, this slide illustrates schematically how dislocations operate and how they make it easy to deform a metal. Normally, if you have a metal like this, and you wanted to move this top half relative to the bottom half, it would be very difficult. It would take a lot of energy and a lot of force to break all the bonds along this line. But there's a trick. What happens is that when we push on top of the top part of the crystal, we can break this bond and this bond. And then this bond will reform with that one. And then this plane of atoms, or this section of atoms, will move forward. And you end up with a line of dangling bonds here, which is the dislocation. Now, as we continue to push on the material, that dislocation moves by swapping, breaking bonds of the adjacent plane and reforming a bond to reforming the bonds by a series of breaking and reforming of bonds. And when it gets to the end, of the crystal, we have a step and the deformation has proceeded, but with a very minimal amount of force being introduced. As I said, if we had to shear all of these bonds all at once, that would take a lot of energy, a lot of force, I should say, to do that. Analogy I kind of like is the caterpillar analogy. A bit of biology. For those of you who know caterpillars, forgive me if I get it wrong. Caterpillars don't have legs. They have a series of what's called prolegs, which are really suckers that keep it stuck to the ground. And so without having the musculature of a leg like a centipede might have, the way a caterpillar moves is by a peristaltic motion. By changing the pressure in its abdomen, it can lift parts of its abdomen, and in this case, it drags its back end forward a little bit, and then it can move by peristalsis, move this ripple along the length of its body until it pops out the end, and it's moved then from here to here. I kind of like that. Other analogies include moving a carpet or tearing a telephone book. Basically, you do it a little bit at a time, and that takes a lot less force at any one point in time. Less power. So I told you about dislocations, which are line defects. Another type of defect that is important for material behavior when subject to neutron bombardment is the point defect. Here's a schematic illustrating how neutrons can cause the displacement of atoms from their lattice site. In this case, we have a high energy neutrons, let's say it's 1 million electron volts, and it comes barreling into the lattice and it collides with an atom a certain probability of that happening, of course, and it can impart some energy, different degrees, because it may glance off or it may be a direct collision, just as you would have with a billiard ball table or a snooker table. Sorry, we are in North America right now, a pool table. So the energy needed to break bonds in atoms is around about 40 eV. So long as the incoming neutron can transfer more than 40 eV energy to the atom, it will cause a displacement. But typically it produces many thousands of eV in the primary knock-on if it's a 1 MeV neutron, and then that goes on to create many displacements. So that's high energy neutrons. But what about thermal neutrons? Are they important? Well, they are a little bit. If you have a thermal neutron, it can interact with the lattice by being absorbed by the atom. Thermal neutrons have energies a fraction of an eV. That's not enough to displace the atom, but the gamma photon that's emitted from the activation of an atom by a thermal neutron has a certain relativistic mass, and the recoil produced can cause displacements, typically about 4 or 5. Now, if that thermal neutron is interacting with nickel, the most common isotope in nickel is nickel 58, and that can then transmute into nickel 59. And nickel 59 is a very unique isotope. It has a very high cross-section for interaction with neutrons of all energies. So any further bombardment with neutrons with nickel 59 produces gamma photons. It has a high probability of producing both gamma photons, protons, which are hydrogen nuclei, and alpha particles, which are helium nuclei. It's important to realize this. The helium one I'll talk about later is very important. So because these particles are very massive relative to the gamma photon, there's a massive recoil energy, and we get a very high number of displacements for each of these events. So when you have nickel around, you get an enhancement of the displacement damage, which creates point defects. I should have mentioned this about point defects. These are the displaced atoms, but there are both displaced atoms, which we call interstitials, and vacancies, which are left behind when that happens. Sorry about that. So not only do you get an enhancement of the displacement damage, but you also deposit a bunch of gas in the matrix. And that can have very serious consequences for materials. And this summarizes what I've just said. Now, these point defects created by atomic displacement can then migrate by solid state diffusion and cause changes in the microstructure. They can cluster and create defects, other defects, planar defects or three-dimensional defects within the metal that changes its properties. And we can use tools to look at this effect. And one common tool is the electron microscope. Now, microscopes originally used to be very crude. I'm sure they had their uses. Here's an example of identifying, characterizing a mammoth. But this is an optical microscope, and it's non-transmission electron microscope, because in order to study metals, we have to shine radiation through the metal in order to reveal what's inside. So just like you would go and get an X-ray, you get an X-ray by shining. You can look at your bone structure by shining X-rays through your body, and it shows where the bones are. And we need to know, in case of metals, where all the defects are in the metal, in the structure. And so therefore we want to have a transmission mode. So here's an early optical microscope, and here's an early transmission electron microscope, which involves shining electrons through pieces of metal and looking at the effect on the trajectory of the electrons. Now, the transmission electron microscope can be used for a number of things. It can be used for fun. We can produce pretty patterns, diffraction patterns. A couple here are shown here. I did this on the CM30 in CNL many years ago. And they can also be used to look at the defects one gets from the radiation damage. So here's a picture or a micrograph caused by, or shown by, shining electrons through a piece of metal. And the little loops we see here, the little ellipses, are actually clusters of atoms or holes in this particular case. And these affect the properties of the material. But we can image them and learn something about the processes, both causing the damage, but also what the damage then does to the rest of the material. Schematically, what's happening, you've got two possibilities. You can either migrate the vacancies. The vacancies can migrate and cluster together. And when they do that and form a platelet, like this, that results in a collapse of the lattice, as we see here. But if the interstitials migrate and form into a platelet and it gets stuffed between the planes of atoms, that causes an expansion of the lattice. Now, a low voltage electron microscope may have enough energy, there may be enough electron energy to transmit electrons through a thin piece of metal. But what if the metal is thicker? Well, then we might use a high voltage microscope, basically beef up the electron energy so we can look through thicker sections. The bonus of using a high voltage microscope is that we can actually also cause damage, and we can look at the damage as we're producing it. So here's me in Stuttgart many years ago. I went there a couple of times at the behest of one of my colleagues who was interested in the diffusion of vacancies. So I did some experiments, and I would basically turn up on the red eye early morning on a Monday morning. I'd work through the whole week, generally till 3 or 4 o'clock every morning, doing experiments, and then fly back on the Friday to get back to my family. The saving grace is a lot of these experiments would take many hours, radiations, and I would get them started, and then I'd be twiddling my thumbs. But the one saving grace of this lab is that they had a beer machine in the basement. So I could go down, have a beer whenever I felt like it, which was generally at 2 o'clock in the morning, which was great. Now, Here's an example of one of the experiments I conducted at Stuttgart, and it shows a dislocation loop, something like this, and I'm irradiating it under particular conditions to look at the mobility, to determine the mobility of the point defects. So this loop itself, there's about 2,000 atoms, I would say. 600 nanometers, yeah. No, 600 atoms across that loop. Just to give you an idea of the scale. And as you can see, it's growing when I irradiate at 300 degrees C, which it just tells me in this particular case that because actually it was a vacancy loop, not an interstitial loop, a vacancy loop, it tells me that my vacancies are mobile at that under those conditions. Not all radiation damage involves dislocation loops, however. Phase changes can also occur. Here's an example of an amorphous phase change in a precipitate in zircaloy. Now, this effect, this amorphous transformation, was first observed by a technician at Chalk River in Brian Cheadle's branch. His name was Ross Gilbert. Now, Ross deserved more credit for making this discovery than he actually got, because a lot of other labs quickly jumped on the bandwagon and all claimed that they just made the same discovery, when it was actually Ross sending them his data, which was galling. But, I mean, to us, it had very little practical importance. Other labs thought it was neat, and they spent a lot of time flogging the dead horses, I would think. One of the labs was a French lab at the Centre d'études nucléaires in Grenoble, and one of the lead scientists there, who I would consider a friend, is Clément Leménion, and he retired some time ago, basically back in 2006. And because I was his friend, colleague, the French asked me, they paid for me to go to Paris and make a presentation in his honor, which I did. And this is one of the slides I developed for his presentation. So knowing he was keen on amorphous transformations, I put the slide together, and this is an amorphous precipitate from one of our calandria tube materials. And what I'm doing next is I'm going to zoom in more detail on the structure. And as we zoom in, we see more detail and then a little bit closer. But now I'm going to zoom out. I changed it from looking into an amorphous precipitate to the M13 globular cluster. And this just illustrates that some of the structures you might look at, it depends on whether you have a telescope or a microscope, but they look very similar. And it's really all a question of the length scale. For more practical applications, here are some micrographs showing the microstructures of a calandria tube in the CANDU reactor, this one, and a pressure tube in the CANDU reactor. Now, the pressure tubes are very important because they're the pressure boundary in the reactor core. So they have to basically stop the core from melting down. So it's very important that they maintain their strength and also their integrity, their dimensions during service life. So because they're subject to very high dose of radiation, it's Chalk River has specialized in the study of what happens to pressure tubes when they're irradiated. And one of the things you should notice is there's all these little black lines in here. And if you remember, I talked about line defects. Really, this is dislocations. These little black lines are the dislocations in pressure tubes, and there's a very high density of dislocations in a cold work pressure tube. And what this means is that the dislocation density is, in this case, there are 4 times 10 to the 14 meters per meter cubed of dislocations in the material. So what do I mean by that? Well, if I take a small sample of pressure tube, this one, for example, which is roughly a cubic centimeter, and I took all the dislocations and joined them end to end, I could stretch them from the Earth to the moon. If I had all of the dislocations in a whole pressure tube, and remember this, oh, well, you wouldn't, I didn't tell you, but there are 380 pressure tubes in a given CANDU reactor. So for a single pressure tube, if I took all the dislocations in a single pressure tube, I could stretch them from here to Pluto and back twice. The last few chapters in my book are about materials issues in different reactor types. So in chapter 14, I talk about heavy water reactors, and CANDU reactor is the most famous one. Now, what distinguishes CANDU reactors from many other reactors is that they run on natural uranium. They do so by, in order to do that, they have heavy water as the coolant, as the moderator, but also most of the internals are made from zirconium alloys. And they're made from zirconium alloys because zirconium is very good at not absorbing neutrons. So that's exactly what you want. You want to preserve your neutron economy. But there are some specialist parts that even in a CANDU reactor, you have to have these other materials in there. Thankfully, not very large volume. And these specialist parts typically are nickel alloys, and nickel alloys are very good spring material. So they're used in certain locations in the CANDU reactor. Probably one of the more important springs is the garter spring. And the garter spring, also known as a spacer, is wrapped around pressure tubes at 4 locations and separates the pressure tube, prevents the pressure tube from sagging and making contact with the cold calandria tube. Now, the pressure tube is hot, it contains the fuel and the coolant, and the calandria tube is cold because it's in contact with the moderator. And if the pressure tube contacted the calandria tube, you'd get a cold spot that would result in blister formation, and the tube would eventually go bang, as it did in 1983 and in 1986. So imagine the concern some people had, not everybody, about 15 years ago when a spacer that after 15 years of service was pulled out of a reactor, got to Chalk River, and it was broken in many pieces. Not a good thing to see. Now, many of my colleagues, many people, certainly in higher management, a lot of the engineers at Sheridan Park said, yeah, but that's going to happen because it gets bashed around in transit. So I said to my staff, I was a manager at the time, I said, go and simulate the damage that you would get of an unirradiated spacer in transit. So here's them doing a simulation in the lab. This is simulating transit in a truck from the reactor to Chalk River Laboratories. As you can see, you can deform the spring, but it's very difficult to break. You can break it, however, by fatiguing it. Now, This is an irradiated bit of spacer. In this case, it has to be the testing has to be done in the lab, and this is a very much gentler form of testing. It's just simply bent, and it breaks very easily. You could break it with your fingers. Not that you would stick your hand in a hot cell; you'd get fried very quickly. So I mentioned about fatiguing. So even the unirradiated sample, you could actually break it just as you can with a not safety pin, with a safety pin, with a paper clip. If you've ever bent a paper clip back and forward, you can break it. And this is what the fracture surface would look like. But in the case of the irradiated spacer, it doesn't look like that at all. It's faceted, and these facets correspond to the grain boundaries. So the unirradiated material deforms eventually and fails eventually by fatigue fracture, but the irradiated one is a brittle intergranular fracture. And I recognized this at the time as helium embrittlement. But I had a hell of a time trying to convince people because they were not convinced that you get much helium in CANDU reactors. But in fact, you do. You get an 100-fold increase in helium compared to any of the US reactors. So why is helium important? Here's two slides. This one is an irradiated sample, 500 dPa. What that means is every atom has been displaced 500 times at this point. We're imaging it now. And what that does is that you displace enough atoms that some of the vacancies created will actually form clusters and increase the porosity of the material, just like when you bake a loaf of bread and it rises. But the grain boundaries are generally pretty clean, and that's because there's no helium involved. However, if you have helium around, it stabilizes these vacancies on the grain boundary, and you get a perforation of the boundary. So normally, if there's no helium, the vacancies will be absorbed by the grain boundary, but not when helium is present. I was illustrating this at a meeting with the CNSC some years ago, and there was staff from OPG and the CNSC, and they all raised the same question. Well, can we do something? What can we do? We've got all this helium in our spacer materials. Can we get rid of it by annealing, for instance? And I said, nope. Helium is like herpes. It is forever. And that's the summary of some interesting stories, some of the more interesting stories that I thought that might give you a chuckle. Do you have any questions?